Right. Yeah, so today we are going to discuss L systems or Lindenmayer systems. Lindenmayer systems, right? So an L system or Lindenmayer system is a type of formal grammar where all possible rules are applied. Yeah, so it is so we are going to we are going to put or we are going to generate these kind of fractal graphs. Yeah, using first of all we are first so we will learn what L system is. Yeah, first of all we have to know that. So after knowing that we will generate these kind of nice fractal branching structures, right? Or different so these kind of nice, so using this let me so you can generate these nice these pictures. So these are two-dimensional pictures, graphs. So here we already discussed two-dimensional. You can add another dimension. So that would be so that would be complex to plot. We have only 2 days to cover this part, so I chose to discuss two-dimensional. So how do we produce these kind of nice graph using L-gram L systems? Okay. So actually, L system is a type of formal grammar where all possible. So here we can see rules. Yeah, these are the rules. Here we have a set of alphabet. So this consists of So V is an alphabet. So it consists of these kind of symbols, and here A B we have only two so character symbols in the alphabet, right? Finitely many symbols here. So here, so for instance, if you consider this, we have 1, 2, 3, 4. So four symbols in this alphabet. So you need to have an alphabet set of alphabet. It could be finite or infinite, right? So here, so let's for simplicity, let's consider finite set of alphabet, right? So V is a finite set of alphabet. So so before talking about the structure of that system, so let's say this guy invented this method. So he's let me go to the let's go to. So if you type L systems, so this is the wiki page. Let me zoom in a little bit. It's so you can go to the wiki to so get an idea about L systems, right? So that's the kind. So it was invented by so it was introduced by L system. L systems were introduced by this Lindemeyer in 1968, right? He's a Hungarian biologist, and he want to describe the behavior of plants or to model the growth process of plant development. So then he developed this L system. Right? He used L system to model the growth of these kind of multicellular organisms. So then can be used to model phylogeny of variety of organisms and can be used to generate these kind of self-similarity. So self-similarity structure. Yeah, fractal-like structure. So we can use L systems to generate these kind of fractal structures, right? So let's see what this L grammar is, right? So L grammar has a structure. L system has a structure. What is the structure? Similar to so Chomsky hierarchy. So L system. So here we are. I think this subject belongs to artificial life. I think artificial life. I think yes. So you can so you can model these kind of so branching structures artificially, right? So for that you need a set of alphabet. So V is the set of alphabet. It consists of symbols to be finite to infinite for simplicity. So let's consider V consists of finite number of symbols, right? So it may have variables. So these are variables. Okay? So these are variables. So why I am saying these variables? So variables, so variables are located in on the left hand side of the rule here, but the constants, constant do not appear on the left hand side, right? So these are the variables, and so these are the symbols of the these are the symbols of the what do you call the alphabet. So these are variables. Let's look at variables. Variables. So there's a rule for those variables. So one has a rule. Zero has a rule. If you have one, so you can apply these rules. If you encounter one, then you have to convert one into one. And if you have zero, if you encounter zero when you read the word, right? This kind of word, if you encounter here, if you read this word from, normally we read words from left to right, right? So what is the first character you encounter when you read this word? One, right? So one is a variable. That means it is for that variable rule is defined. So rule is defined. That's why we call it is a variable, right? So what is the rule? When you read a word, when you encounter this character one, then you have to convert that one to one. So when you read this word, you encounter first character, right? Which is one. One. You have to convert. So one is replaced with double one. So one. And here these are constants. These are constants. Rules are not defined for constants, right? So if you encounter those kind of constant, you just leave as it is here. So here, first one, when you read this word, okay, first one is one. You encounter one. Then so there's a rule for that character, right? Then Then convert this one to, yeah, change this to 1 1. Yeah, let's change this to 1 1. And the second character of this word is open square bracket. So it is a constant. Then you have to copy this down. Yeah, so there is no rule for that. That's why we call it constant, right? So then copy. Yeah, leave as it is. Yeah, so leave as it is. And the next one, next symbol is zero. There's a rule for that symbol. What is that symbol? What is the rule? Yeah, so you have to convert zero to into, yeah, this one. Yeah. So yeah, zero is converted to one, this block here. Yeah, so you have to copy that block. Yeah, something like that. You can generate words recursively, right? So for that you need an initial word. So here you have variables. Yeah, so these are, so this is your set of alphabet. It consists of two character symbols A and B. Both are variables. If they are variables, there are rules for those things. Yep. So these are the rules. All right. So there are no, yeah, a constant in this alphabet, right? Okay. So this is the initial word. This is your initial word. Yeah. So from this initial word, so you need to have an initial word to execute this algorithm. So yeah, so linear system consists of these three things. So what are the things? What are the set of symbols or set of? So this is the alphabet set, and this is your initial word. You know it represents the initial word. Yeah. So an empty word. Yeah, initial word, and this is the production. So the set of rules. So you can define these kind of so with with symbols in alphabet, you can define these kind of so ordered pairs, these kind of ordered pairs. So p is a rule, yeah, P is another word, and A is an character, is a symbol in this alphabet set. And if you have this kind of ordered pair, so A is a variable, yeah. So because we have a rule, so A is a variable, right? A is a variable. So if it is a variable, yeah, so there's a rule for that, right? So these kind of structure is called Lindemeyer systems, right? So these are the examples. Yeah. So first one is trivia. If you go to Wikipedia, right, you will see you can see there are many examples. Actually, so before discussing discussing these examples, I want to mention that so these elk systems can be deterministic. Yeah, these so deterministic or stochastic or context sensitive, context insensitive, or parametric or not here. So look at this. So yeah, this is deterministic. So these are the examples of deterministic models, L systems. And if you scroll down a bit, can this is deterministic. Yep. So this one also deterministic. Yep. Stick. Yep. So there's another other L systems which is called stochastic. So when you define rules, so this so here, so if you encounter zero in when you read a word, when you encounter zero, you have to convert zero into this word definitely. But if you put if you if you specify with the probability like this, right? There's a 50% chance of converting zero into this word, and here also. So it could be zero could be converted into so this word with this probability or itself with this probability. So these kind of IL systems are called stochastic systems, systems, right? Stochastic. So here we have a probability. So earlier case, when you define a rule, there is no probability exactly when you encounter this character symbol. Definitely that is converted to this here. So, but if you specify a certain probability, so then, so we know that when you look at the nature, right? When you look at the nature, we get different branching structures, right? And they are not are the same. They are not are the same. So definitely, so when you include this probability term here, then we get different branching structure. This one is deterministic. We get exactly the same structure, but if you specify with this with the probability, right, probability, then we get different structures here, not this one all the time, right? So those are stochastic L systems, L systems. All right. Stochastic, and the other one is context sensitive grammars. So here, so when you read a word, right? Let's say you encounter a, right? So this a depends. When so you encounter a, right? So a take. All right. So this is your word. Say be like this. So let's read from here. So let's assume these are variables. That means you have these characters. So because they are variables, so then rules are defined for those characters, symbols, right? Some word here, and let's assume this is probability. No, this is deterministic system. So if you encounter B, it is converted exactly to this word here, right? Without any probability here. Probability is 100%, right? 100%. Yeah. So C, another variable C. So another word, convert to another word. But if you have A, right? Let's say when you so A is another variable. So when you define, so A is converted to double A is converted to double A whenever and always A looking at his neighbor. Whenever B is his left neighbor and C is his right leg, then yeah, so if you have this so if you have so A is converted to double A whenever A having these neighbors. That's why A having these neighbors. That's why we call it context sensitive grammars. Otherwise it won't convert it won't be converted to double A. Transform A to double A whenever A having these neighbors, B on the left side and C on the right side. Because between, so like that, so this one depends on the, so neighbors, so this is context sensitive grammars, so it's not only symbol it is modified, but also symbols on the string appearing, so appearing, that is very important, you can define in that way, right? And the other type is, this is context insensitive grammars. These are context insensitive. So we don't check the neighbor when you convert X into this, right? We don't check that. So this is context insensitive grammars. And these are context sensitive grammars, right? Right. Always look at the neighbors, right? And the other grammar is parametric. You can include a parameter into these variables, right? So, so let me remove this. So like this here. So this is the variable. So these are the symbols in our alphabet, right? And you can define these symbols with these kind of parameters. Okay? So earlier we didn't have those parameter type grammars, right? But you can consider defining grammars with parameters like this. Let's say this is x coordinate and y coordinate, right? And this one. So you can define a rule like this here. Here. So you convert symbol A whenever x coordinate is equal to 0. So right when x coordinate of this this symbol, so this symbol is accompanied with this parameters, right? This symbol is accompanied with these parameters. So this is x coordinate and y coordinate, right? Then you can define the production rule like this here. So when you read a word, right? If you encounter A, and A consists of these parameters, and if you have 0 for x coordinate, then you convert this symbol to this word here. So let's say, for instance, if you have this in a word, right? So this will be converted to a of 1 comma, so a of 1 comma y plus 1. Y plus 1 is, this is y coordinate. Y plus 1 is 3, and b of 2 comma 3. Yeah. So these are complicated. Yeah. So like that. Yeah. So there's another grammar style. Yeah. So this is by directional grammars. So this, I think this type of grammar is not that famous. I think these are very famous. But in our today's session or tomorrow, today and tomorrow, next week session, we just focus only the not stochastic. We just focus only the deterministic grammars, deterministic case, yeah, the context insensitive grammars, stochastic grammars. Yeah, you can definitely define rules with the probability, right? So that when you do that, yeah, you get different structures because there's a probability there, right? So when you look at the nature, when you look at your environment, you will see, you can notice different branching structures. Yeah, so definitely there's a probability with these rules, right? With these rules, but uh, for uh, in our class, we discuss only this deterministic context in insensitive yeah L systems. Okay, so post the video. Yeah, so algae. Yep, so Lindemeyer, originally, developed an L system for growth of algae, right? So, so he consider two symbols in the alphabet set. Yeah, so we consist of two elements. Yep. So what are those? This could be any, not only. So you can put the smiley, smile face. So these symbols are stars, right? So anyway, this set has. I will take a set AB. Yep. So A and B, two symbols, right? And all symbols are variables. That means all so each symbol has a rule. So if you read a word, when you encounter this symbol, then this symbol is converted to which one? AB. Yeah, like that you can define. You can define any rule. Yeah, let's convert this one A, B, A, right? A, B, A, right? Then you can define, you can change this word. Yeah. Anyway, you have to use only these two symbols because in alphabet consists of two characters, which are A and B, right? So using A and B, you can define any rule. Yeah, A is converted to A, A, B, A like that. Yep. And B is converted to another one. Yeah. So A, B, B. Can define any rule, right? So I will use this rule, right? I will stick to this, the Lindemayer's rule. Yep. So, all right. So these are the rules because we have only two variables, right? No constants, right? So A is converted to AB and B is converted to A, right? Okay, so this is the axiom. Axiom is A, which is our initial word, right? Axiom. So without axiom, in mathematics, without axiom, you cannot prove theorems. So you need, right? So axioms are very important. right? So you cannot develop any theorems with. So so without an initial word, yeah, you can generate words, rewrite words. Right? Okay. So we start off with this word, right? This is our initial word or initial rewrite. Initial word, right? Okay. 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 Let's read this word. Okay. A. When you read this word, you encounter this symbol. Is there's a rule? Yeah, yes, it is. Yeah, there's a rule because it is a variable, right? So what is that rule? If this is the rule, if you have A, then A is replaced with AB. Okay, then A is converted to AB. This is your first rewrite. I will denote it like this word. Yeah, rewrite one. As this, yeah, I will denote this one as this, yeah. So this is the first initial, this is the initial word, and this is the first rewrite. Okay. And what is the second rewrite? How do you get the second rewrite? Yeah, let's read this from left to right. Yeah. So starting from this side. Yeah. So we encounter the symbol A has a rule. Yeah. So A is converted to AB. Yeah. So let's write A becomes AB. AB. Then what is the next symbol? B. If you have B, yeah, there's a rule for B because it is a variable. Yep, so B is converted to A. Yep, so then this B is converted to A. So this is my second rewrite. Second rewrite, I will denote it as W sub 2. Yep, so second rewrite. Yeah, W. So this is W sub 2. Yeah, second rewrite. Yeah, iteratively, you can generate, so many rewrites. Yep. So now from this one, you can generate the next rewrite. Let's generate that. Yep. So let's read this. When you read the word second rewrite, when you read this word, so what is the first character or first symbol you encounter? A, yes, A. If you have A, you have to change it to AB. Yeah, so that's right. So A is replaced with is AB. Yeah, yeah, A is done. And next character or symbol is B. B is converted to A. It's done. Yep. So next one, A. A is converted to A. So this is your third rewrite. I will denote it as like that. Yeah, you can generate. Yeah, so rewrites. This is the this is this one third, fourth rewrite, fifth, sixth, and so on and so forth. Right. Okay. So if you have rules with an initial word, right? So then you can generate these words iteratively, right? Yes. So let's look at another example. This one, fractal tree. Yep. Yep. So V consists of two elements, two symbols, but no, four symbols actually. Yeah, four, one, no, zero, comma, one, and there are another two. Yeah, open square bracket, close square bracket. Right? Yeah, so this is our This is our alphabet, right? Okay, so this alphabet, so first two, 0 and 1 are called variables. Why? So there are rules for those characters, those symbols here. These are the rules. That's why we call them, yeah, as variables. Others, yeah, constants. Yep. So no rules for these constants. Yep. So no rules defined for constants, right? Okay. Okay. So yeah. So this is your axiom. Yeah. Initial word. I will denote as initial word. Yeah. Yeah. So using this initial word, I can generate other iteratives, other rewrites by applying these rules. Yep. So how do you do that? Yeah. Let's do this. Yep, so here look at this. So if you have one, you have to convert that one to double one and zero this block here. Yep, so one this block. Okay, okay, yeah, this is your first initial word. Yeah, how do you get the next one? Yep, so when you read this one, you encounter there is only one character in this word, yeah, which is zero. So zero is a variable. So there's a rule for that because it is a variable. Yeah, so this is the rule. So what is that? Yeah, zero is replaced with. Yeah, let's apply this rule. Okay, when you apply this rule, yeah, so zero is converted to this. Yeah, so this is the first rewrite. Yeah. Yep. So if you have first, you can generate the second. If you have second, you can generate the third, and so on and so forth, right? Yep, so let's read this to generate the second rewrite. Yep, so one. Yep, so one is converted to double one here. And yeah, open square bracket, which is not a variable because there are no rules for open square bracket. That's why if you have a constant or no rules, yeah, just copy that down as it is. So just put open bracket. Okay. Then next character is zero. Yeah, zero is a variable. Why I'm saying it is a variable? Yeah, it has a rule. So let's apply rule for zero. Yeah, this is the rule for zero. Yeah, you have to copy this. Yeah, so, yeah, copy that block here, this one. And next symbol, yeah, close bracket. Close bracket is a constant, no rule for that. Yeah, copy that. And zero again, let's apply this rule. Zero is a variable, it has a rule. Yeah, let's apply that rule. Yep, so this rule. So this is the second rewrite. I think you understand how to obtain these rewrites. Yep, so now we are going to, yep, so in the practical session, I think you are going to write Octave code to generate these rewrites, right? So first of all, you have to define these symbols. Yeah, you can try now. Yep. Yep. So first, so this is your alphabet. Define these symbols in Octave, right? And define the initial word and define these rules using for loops and all. Yeah, so can you obtain these rewrites? The second rewrite, third rewrite. Let's say I want to see the 10th rewrite. Can you? Yeah, second. Yeah, so another one, coach curve. Yep, so variant coach curve. Yep, so here in the set of alphabet, yeah, which consists of three characters. F is a variable, and there are two constants. Yeah, so because we have only one variable, yeah, there is only one. Yeah, so rule for only one rule for F. Yeah, so and this is your initial word F, right? Yes. Then yeah, you can generate rewrite. So using this, yeah, this is the next rewrite, and this is the first rewrite, and this is the initial word axiom or word initial word. You can first rewrite, second rewrite, like that. You can generate. So how do you? So this is the third rewrite. So how do you write a code to obtain these words? Yeah, so that is one of tasks. Tasks. Okay. So any questions so far? Yep. So let me. Yes. Now we are going to visualize our rewrites these words, right? So we want to visualize. So this is also here very difficult to memorize here. So if it is a mechanism to visualize this graph, so when I say something, let's say tree, so you can visualize the picture of tree, right? So like that, when you pronounce this word, so can we visualize, yeah, this word? Yeah, we can. Yeah, so we can do that. So for that, you have to define these things, these symbols meaningfully. How do you define that? Yeah, so if you go to Wiki, yep, so, so yeah, let's click going. Yep, so yeah, let's do this. Yep. Yep, so yep, you can visualize these words. So these are words, right? These are words. Yeah, so this is the initial word and first iterative, and this is the second iterative word or second rewrite. So how do you visualize these? Yeah, so words. Is there's a way to visualize these words? Yeah, there's a way. So if you define these symbols meaningfully, yeah, you can visualize these words. How do you do that? Yeah, so here F. So F is is only one, is the one and only variable in the alphabet, right? Yeah, you can define these symbols meaningfully. Yep. So you can define as draw forward F. If you encounter F, yeah, you can say draw forward by 1 centimeter or 1 unit, right? 1 centimeter, right? And if you encounter plus, yeah, turn right, no, turn plus, yeah, turn left by 90 degrees. Yeah, if you encounter when you read this word, yeah, when you read this word, so this means plus means, yeah, so turn left by 90 degrees. And so minus, if you define minus as turn right by 90 degrees, yeah, you can, visualize these words, yeah, nicely. How do you do? Yeah, let's do it from here. Yeah, so let's say, yeah, so, yeah, your pen is here, right? You are facing this direction, right? Yeah, so here, this is your pen. Yeah, so this is the pointer. Yep. So you start off with start off at this point. Uh-huh. Facing in this direction, right? Okay, so first word, yeah, so F, yeah, draw forward by 1 centimeter. Yeah, so this is the so if you have F, yep, so you can get this, yeah, you can visualize as like this. Yeah. All right, let's say if you have a word like this, let's say what is the graph of that, right? K, K, right? Yeah, I will draw in different color. Yeah, so right. Okay, facing in this direction. Let's assume facing in this direction, and the initial point is at the start of at this origin, right? Yeah. Move forward or draw forward by 1 centimeter. Yeah, you can mark your paper. Yeah, so 1 centimeter. He is still facing in this direction, and then turn left by 90 degrees left. Yeah, this is he's facing this direction. Now he turns left by 90 degrees. Now he's facing in this direction. Okay, and then draw forward by 1 centimeter. Yeah, so my draw forward by 1 centimeter. Yes, yes, and he is still facing north. Yeah, let's say this is north. Uh-huh. Then, yep, so here you encounter this symbol negative. Yeah, negative means, yeah, turn left or turn right by 90 degrees. Yeah, and turns, yeah, he's facing this direction now, but his position is here, right? And move forward or draw forward by 1 centimeter. That 1 centimeter still facing this side. Uh, yeah, this is west or east. East. Yeah. Yeah. So and what is yeah. So then again negative negative. Yeah. Turn negative means yeah. Turn right by 90 degrees. Now he is turning right by 90 degrees. Yeah. So he's facing this direction, but he is at this location. Yeah, move forward, draw forward by 1 centimeter, and again turn left, yeah, this side, and and yeah, so that's why you get this. So like that, yeah, you can visualize these words, right? Like that, you can visualize for this, yeah, this word. Uh, Okay, this when you specify these symbols, these characters in the alphabet, in the alphabet, in this way, yeah, you can visualize these words. This way. Okay, that's why you get these two-dimensional blocks, right? Yeah, let's look at this one here. Okay, so this is a famous graph again. Yep. She ski. Yep. So let me I took from here. Yeah. So here we go. Yep. Yeah. So here. So yep. So yeah. So then yeah, you have four characters in your alphabet, and two of them are variables, and two of them are constants. And this is your initial word, right? And because we have two variables, yeah, we have two rules. right? So the turning, yeah, so this the angle the turtle turns, right? So you can consider as a turtle here. So turtle is moving on the two-dimensional plane, right? XY. So yeah, so this is XY plane. So this is turtle with a pen. Yeah, so moving on this plane, two-dimensional plane. This is X coordinate, Y coordinate. Yeah, so initially starting at turtle is starting at this point and facing in this direction. Right. Yep. So starting at this, and turtle has a pen. Which color? Let's say green color. Yep. So when turtle moves, then at the same time, it marks this plan with his pen. Yeah. So right. Hmm. Yeah. So F and G. Yeah. So then yeah. So we have four symbols in the alphabet, and two of them are variables. And for variables, we know we have rules, right? And two constants are there. So if you define f and g in this way, yeah, draw forward. If you meet, yes, let's look at yeah, f and g both meet. Yeah, draw forward and plus means yeah. So turn left by this angle 120 degrees, and minus means yep. So turn right by this angle. Then yeah. So this is the second rewrite. So when you visualize the rewrite, the second rewrite, you get this picture. When you define f and g and angles in this way, yeah, you get this picture. This is the fourth rewrite. Like that, you can increase the number of iteration. Yeah, you get nice triangle. This triangle has a special name. Yep. So this is called how do you pronounce this? Sierpinski, yeah, triangle. Yep. So yeah. So like that, I think you can generate a few. Yeah. So today, yeah. So next week, yeah, we will generate these kind of nice, yeah, graphs. So this week, I think how do we generate? So I will tell you. So how do you, yeah. So how do you how do you obtain these rewrites? And if you define, yeah. So if these symbols meaningfully, right, then you can visualize these rewrites. Yeah. So how do you write a code for that? Yeah. So that's my question. I think we have an expert in this. I think she's very good at these things. I think you are one of our teachers. Yeah. Avansika knows everything. Yeah, she's an expert in these things. Yeah, she She produced, I think, a lot of nice pictures. I think there was an exhibition last week. I didn't, I unfortunately, because of your lecture, I couldn't attend that. Yeah, nice exhibition. So she generated, I think, nice, meaningful pictures. I think you have seen those pictures, right? Nice, nice using these algorithms. computer algorithms. Yeah, she generated nice pictures. Do you have a chance to talk to him and get her knowledge? Yep. So try to talk to her and the knowledge. Yep. So, okay. All right. Another one. Fractal plans. Yeah. So you can, if you go to wiki, yeah, here we remove my right ticks. Yeah, so here, so if you define these symbols, yep, so then you can visualize uh, those rewrites meaningfully, as I said before. Yeah, yeah, this is the niche. I don't know, n is two. Yeah, n is two. When you increase the number of iteration, you get nice fractal structures. Oh, and dragon curves. Yeah, if you have time, don't know if you have time, yeah, you can play with. Yeah, so after today's session, you can generate these outside thing. Yeah, so let's see how it is. Yeah, yeah, dragon curve. Yeah, forward and by this angle. Yeah, so if you define rules like this, yeah, you can. Uh, yeah, so, and there's another, yeah, another example. Yeah, so you can code. So when you define, you can change these rules and see the difference, right? And if you have, so here you have two variables, yes, and four constants, and this is the initial word, and you specify the angle. Yeah, with this angle, you get, yeah, you have this so this branching structure here. The next week, I think you will generate these branching structures. Today, you will generate, these kind of, you can generate these kind of nice books. Yeah. So this is the animation of that. So this is the sixth iterative visualization of six iterative. Six rewrite. Yeah, you can increase this number here. Let's say 100. Yeah, then you can see a lot of leaves and everything. When you increase by the computational power, that depends on the computation power you have. Right. So, right. Yeah. So we won't discuss. Yeah. So better include the probability part. So because in the nature we see different structures. They are not the same. Right. So if you include the probability, when you define these rules, include a probability, there's a probability. Then, so this may, this, you get different structure, yeah, all the time. Yeah. If you include a probability bit here, right? All right. So that was the introduction. Yeah, that was the introduction. Let me pause the video. Yeah, to understand the concept, let's do this by hand. Later, you will code this, right? You will use Octave to write a small code to generate rewrites as well as the grams, turtle grams, right? Okay, so right. Okay. No, before that, me as pause, yeah, pause. Yeah. So, any questions, any doubts, any questions? Yeah, related to this. Yeah. Any questions? Yes. Any questions? Any doubts? Any questions? Yes. Yeah, it's time to ask questions. Any questions? Yeah, can you fill this out for me? Yep. By hand, it's fine. Yep. Any question? Yeah, now you can ask questions. Yeah. So did I upload this to LMS? Yeah, upload to this. Yeah. Now you can ask questions. Let me upload. Yep. So please ask questions if you have any questions. Ah, yes, I uploaded, already uploaded. Tutorial one. Yeah, I uploaded this. Yes. Okay. Yeah, without taking much time, let's do this by hand quickly. Right. So if all right. So the initial word is given here. A word is given, right? So in the below table, calculate the turtle graph. Okay, now we are going to visualize this word. The word is given. Uh-huh. Now we are going to visualize. For that, you have to find the coordinates, xy coordinates. So this is x, y. Initially turtle start. Yeah, initial state of the turtle is given. The turtle is located at the origin here, and he's facing upward direction. Okay, he's facing upward direction. Yeah, 90 degrees. So we measure angles from x-axis. Yeah, 90 degrees. Now he's facing northward. Okay, north side. Okay, right. So his original location is here, and the corresponding. Yeah. So okay, right. Initial state is given. Right. When you Yeah, let's read this word. Okay. What is the first character you encounter? F. Yeah. So, right. So, if you want to visualize this word, then you have to specify. Yeah. So, the symbols meaningfully. Yeah. F means move forward. Yeah. Draw forward or move forward. Move forward by D, or draw forward by D centimeters, let's say by centimeters or D units, right? And F plus means turn left by what is the angle, and angle is given 90 degrees, and minus turn right by 90 degrees. Okay, let's read this. Let me record this. Thank you. Yep. So now we are going to visualize this word is given, right? So for a given, so we are going to visualize this word. To visualize this word, you have to define. Yep. So the symbols meaningfully. Yeah, there are four symbols. No, three symbols. Yeah, so so for three symbols, yeah, F means, yeah, move forward by the centimeters, right? And plus means turn left by angle is given delta by delta angle. Delta is given 90 degrees. Turn right by 90 degrees. Okay. Okay, let's try to visualize this. For that, you have to find the coordinates. Okay, initial state of the turtle is here and it is facing upward direction, right? Okay, right. So, okay, let's read this word. First character is this. F move forward by D is specified, right? 1 centimeter, right? So move forward by 1 centimeter. Yep. So then his coordinate would be what happened to the x coordinate? X coordinate remains the same, but y coordinate changes to 1 centimeter one, right? What happened to the angle? Angle is still facing upward direction. Angle is still 90 degrees, right? Okay. The next character, when you read from left to right, when you read this word from left to right, so we done this character. We done the first character. Let me mark that. Yeah, I done this first character. The next one is plus. Yeah, yeah. Plus means turn left by 90 degrees. Turn left. Then he's facing this side. Yep. So just turning left, right? So this remains the same. These coordinates remain the same. But this angle, what happened to the angle? Angle change. Angle changes to, yep, can see options. Okay. Plus turn left. Oh, sorry, turn not turn right. Turn left. Sorry. Yep. So turn left this side. Turn left is this side. Okay. Okay. Turn left here 90 degrees. Turtle is turning left. Then the angle. Sorry. Thank you. Thank you very much. Yeah. 180. Okay. Now, the turtle moving forward. Yes, moving forward by 1 centimeter. When you move forward by 1 centimeter, what happened to the y? Y remains the same. No, yeah, y remains the same. X changes to -1. Yeah, so this is 1 centimeter. Yeah, -1. Like that, yeah, you can find these coordinates as well as the angle, right? The turtle is still facing this side, right? 180 remains the same. And plus again, turn plus means turn left by 90 degrees. Okay, this side, 90 degrees. Okay, now the angle would be angle changes to 270. Yeah, 270. 270 degrees. These coordinates remain the same. Yeah. So move forward, yeah, so you understand, yeah. Move forward, this remains the same. Yeah, so then when you move down, what happened to y code? Y coordinate changes to 0. X coordinate remains the same. Yeah. Yeah. So turn left, right, turn left. Yep. So left. Yeah. So this side. Yeah. So turn left remains the same. But the angle 360. Yeah. And move forward. Come back to the, yeah. Come back to the original position with this angle. Yeah. So the, yeah, journey of the turtle. So what is the plot of the journey of the turtle? Yep. So it's a square. Yep. So then the visualization, when you define these symbols in this manner, right, then you can visualize this way, right? So this word, right? So if you have a complex word like this, rewrite like this, like you can visualize. Then how do you code this? How do you write a code for this? Yep. So then you will work. So you have to write a code for this. How do you do that? So this is the turtle. Yep. So you can draw this. Yep. So then this. The question is, how do you write a MATLAB or Octave code